This conference will now be recorded.
All right, good afternoon, everyone. Thank you for joining us today for our webinar on remote power delivery, power over Ethernet versus powered hybrid fiber. My name is Eric Althazer, Marketing Manager of Programs and Services here at Optical Cable. For everyone's convenience, all lines have been placed on mute to prevent any background noise. If you have a question throughout the webinar today, please email us at info@occfiber.com. That email address is available at the top of each slide for your convenience as well. For all of our Big C credential holders on the call today, this presentation also includes one Big C credit. In order to qualify for the credit, you will need to stay for the end of the presentation when directions are given on how to obtain the credits. We're excited to present to you, and giving our presentation today is Jamie Calloway. Jamie is a product management specialist and RCDD here at Optical Cable based out of our Asheville location. Jamie, I'll turn it over to you.
Okay, thank you, Eric. First, I'd like to just again thank you everyone for joining today. The topic of the presentation today is remote power delivery, PoE versus powered hybrid fiber. And hopefully many of you were able to attend the presentation last week on OCC's slimline hybrid cable. This presentation is actually a little more technical, a little deeper dive into the how-tos, if you will, of deploying that type of cable. But the first part of the presentation, we're actually going to just focus on power over Ethernet, which there are actually a lot of similarities. And you notice in the subline there, PoE versus powered fiber or powered hybrid fiber, they're really complementary. So it's not an either or. So, and as we go through the first section or the first half on PoE, I think you're going to see a lot of similarities, and it's really kind of a foundation, if you will, as we get into the powered fiber discussion. So with that, we'll move right along. First of all, I'd like to just provide a brief overview of OCC. The company was founded in 1983. There are 3 locations. Our headquarters in Roanoke, Virginia, which is also where our fiber optic cable is manufactured. Second location is Asheville, North Carolina, which is where I'm located, which is where most of our copper and fiber connectivity is manufactured. And then our location in Dallas, Texas, which is where most of our commercial, military, harsh environment type products are assembled. And all 3 locations are ISO 9001 certified, so, or registered, I should say. So, and also at the bottom there, you can see just the various marketplaces that we serve, which is really the majority of the markets, you know, from commercial to military, broadcast, and so forth. So we have a wide variety of copper and fiber optic products, you know, that really fit well with all of these industries. So with that, we'll just provide an overview of what we're going to talk about today. The first is I just want to go over some applications that really are applicable to both PoE and powered fiber. Many of those, or probably most, you know, everyone is familiar with. And then some basic terms, some calculations that we're going to be using in some of our examples. And then limitations that really are limitations of PoE and powered fiber, and then some key features of PoE systems. And I think a key reason for that, you know, for really going into the detail of the features of PoE is because one of the things I want to emphasize right away is that PoE is basically a plug and play technology. It's been around for many years. Actually, 2003 was when it was initially introduced. But as you start deploying what we call powered fiber or hybrid fiber, if you will, there's really a lot of more manual calculation, more planning that's involved. So that's why I really want to kind of touch on that. And then some planning and deployment considerations for both. And then PoE versus powered fiber. And I already mentioned, even though I use that term versus, they're really complementary. And what happens really is you have much more versatility in your network design when you utilize both. So we're going to get right into it. The first is some of the applications. And again, you know, these applications you see listed here, not necessarily listed in order of deployment or popularity, but for sure, wireless access point is one of the most common, you know, remotely powered devices. Also, 5G active antenna systems or DAS solutions. You know, and I think we're just going to see a substantial growth in the coming years of 5G systems. LED lighting is another growing application for remote power, as well as IP cameras and other what we call IoT and Internet of Things devices, access controls, for example. All of those devices require power. And for sure, local power is not always available. And so the remote power delivery oftentimes is the most economical, and also it's just really the most practical, because local power is not always available for these type of devices, or just not practical to be installed at certain locations. So as I mentioned, we're going to cover just a few terms and some calculations, and basically, and primarily this is going to think just to help understand the relationship, especially when we're getting to talking about how do you actually calculate, for example, how far you can go, what conductor size you need. Specifically, we're talking about for the powered fiber. So I think it helps to understand these basic terms. Some of you may be very familiar with this, others not so much. But really, we're going to talk about, we're looking at current, voltage, resistance, which is expressed in ohms, and then power, which is expressed in watts. I think this table here, hopefully you're seeing my animations and graphics in real time. But I think this Ohm's law will really kind of help show the relationship of those four parameters, if you will. For example, you look at the top left quadrant, power, for example. You can see any two of those variables, having those two, you can calculate your power levels. Current times resistance, for example, voltage, current, and so on. So again, that just kind of is a nice visual. No worries, you don't have to memorize that, or it's not really necessary to know that in detail to be able to do what we're going to do today. But again, I think it's just a good visual representation how those they interact. So some basic terms. Hybrid cable. Basically what we're talking about is it's a cable that contains both the copper and optical fiber under one jacket. And again, that was the product that we presented last week with our slimline hybrid cable. And then really a powered fiber, we use that term, which is really just another term for a hybrid cable. And then, and I'm going to be using that term, I think, from this point on. I'll just refer to it as powered fiber. And then remote power. Basically, as I said before, it's a method for delivering power to a device from a centralized location using PoE or hybrid cable, which instead of local AC power, which again, it could be because AC power is not available. It could be too expensive or just not practical to install at that location. And then the final two terms, PSE and PD. PSE basically is a power sourcing equipment, which an example of that would be an Ethernet PoE switch. And then PD, a power device, which an example could be a wireless access point or an IP camera. And those two terms are really found predominantly or primarily in the IEEE PoE standard. So the next thing is limitations of both PoE and powered fiber. One is the DC voltage range, and some of these limitations are really intentional. The DC voltage range is, for the applications we're discussing today, are generally limited to 60 volts. And the reason for that is to comply with the SDLV or safety extra low voltage requirements defined by the IEC 60950-1 and the NEC class 2 power source limitations. And those are also defined in the TIA document that we'll refer to a little bit later, TSB 184, for delivering remote power or over twisted pair cabling. So 60 volt DC, or again, I'll just go ahead and say this as well. As we talk about class 2, that obviously applies to alternating as well as direct current, but our conversation today is limited to direct current. And again, that's because PoE is designed to support DC power, and most of the devices that we're really referring to that we would be supplying power to are DC or direct current. So our power limitation is 100 volt amp or 100 watts. Our distance, 100 meters, and this is critical. That really only applies to PoEs. Most of you probably know that, and that's really one of the downsides now as fiber is being deployed deeper into the network, closer to the device. Obviously fiber can go much greater distances than copper cable, but we're still limited with PoE to that 100 meters. So this is a real reason, or a key reason, why we're seeing growth, tremendous growth of powered fiber, if you will, is because of that 100 meter distance limitation. So With powered fiber, we're no longer limited to that, but there are still some limitations, which we'll get into a little bit later. And then there's some other limitations, and it's bundle sizes for one. And we're going to look at two documents. One is a TIA document, which is, by the way, TIA, Telecommunications Industry Association. It's a TSB 184 that I referenced earlier. And then the NEC document, the NEC 725.144. So again, with the NEC class 2 power source limitations, basically 100 watts. Just to give you an example, our max operating current at 100 watts and 60 volts, we're looking at a maximum current of 1.66 amps. So I will say that, as you see there, generally class 2 power supplies are limited to 57 volts maximum at 1.75 amps, 100 watts. So, but again, you know, the code does allow for greater current at lower voltages, but again, mostly what we're looking at is class 2 supplies at 57 volts. We're typically powering 48 volt devices, but if you want more detail, you can refer to the NEC to table 11B for class 2 and 3. DC power source limitations, also 11A covers AC, but I think, again, I just want to limit that to what we're discussing today. The next is some key features of the IEEE, which the latest standard is IEEE 802.3 BT standard. Really what these are is these features really enable the plug and play nature of PoE. First is detection. Basically what it does is it determines whether a valid device is capable of receiving power over Ethernet and before connecting power to it. So there's this handshaking between the PSE and the PD. And then there's a classification function, which basically determines how much power the device requires and how much power is available. And then there's the startup, operation, disconnection. Basically, those are design protocols that ensure safe, orderly operation and to address any abnormal events such as power overload or short circuit, for example. So again, key point of this is, you know, really, I mean, those of you who have implemented PoE may, you know, take exception, say, well, it's not always totally plug and play. There are issues, but generally speaking, it's pretty much a plug and play. The devices, you know, do that handshaking and allocate the power and so forth, and then control an orderly startup and whatnot. But really, the key point is when you get into powered fiber, those things don't occur. That's a manual intervention. So basically, the designer, the installer, they have to ensure that all those things occur. You know, there's no short circuit condition, for example, and the proper selection of your power supply to ensure that you're going to be able to deliver adequate power and whatnot. So anyway, and we'll talk about that in more detail later. So the next thing is what's new in the latest PoE standard. I will say this, that what's new is there's several things, but the latest standard actually is not so new anymore. It was actually released in 2018, but it was a major leap over the previous standards. One is there's more power available at the PSE, the power supply, if you will, up to 90 watts. That's 3 times the previous power level of the 802.3 AT standard. A key advancement is the new standard supports 4-pair power delivery. Previous standards only utilized 2 of the 4 pairs in a twisted pair cable. And then there's more intelligence. And one of those examples is better power management and increased efficiency. One example, again, is lower standby current. This is really important for applications such as PoE lighting. And there's also an optional extended power mode. This basically provides for 90 watts of power up to the PD for channel links that are less than 100 meters. And you say, well, I thought it supplied 90 watts. Well, as you'll see in the next slide, basically the 90 watts is at the PSE. The PoE accounts or always assumes a worst case 100 meter distance limitation. So basically with 90 watts, we're able to deliver 71 watts to the device over 100 meters of cable. So this optional power mode, it can actually detect if there's shorter lengths of cabling. And basically instead of allocating that additional budget, if you will, for loss, it can allocate it to the device. So that's how, you know, we're able to work around that. So, and this is the table I was referring to. I think this really provides a good overview. I know it's a lot of numbers here, but I think it provides a good overview of the PoE, really the evolution of PoE. I think, as I mentioned, the original standard, excuse me, was released back in 2003. It's hard to believe it's been 17 years ago, but that's really PoE was introduced into the marketplace to provide power for voice over IP phones. And it originally provided the maximum power at the PSE of 15.4 watts, and it was capable of delivering approximately 13 watts of power over 100 meters of twisted pair cabling at 350 milliamps current, by the way. So it's, as you see, the evolution, the subsequent standard, which was released in 2009, it basically nearly doubled the power level, 30 watts, and then we were able to deliver 25.5 watts to a device. Our current jumped up to 600 milliamps. Both of those standards still utilize 2 pairs, but in 2018, the current standard, 802.3 BT, tripled the power level from 30 to 90 watts, and we're also using up to 4 pairs in certain classifications to deliver the power. And so as you can see for the BT standard there, the different classes, basically we have a minimum power of 4 watts at the PSE all the way up to 90 watts. And then we're delivering a minimum of 3.84 watts to the device up to 71.3 watts. You also notice our current, and I know this is kind of a lot of technical stuff, and of course I don't expect you to memorize it, but we increased our current level, not so much this time, but from 600 to 866 milliamps. And that doesn't seem like a huge jump, but again, we doubled the number of pairs as well. So we're really carrying more than twice the amount of current. And this current level, is just numbers right now as I'm speaking, but we're going to see that's going to really matter, and it comes into play later on as we discuss some issues such as cable bundling and whatnot. So some of you may wonder, like, well, I understand, a twisted pair cable that carries basically its power over Ethernet, so that means we're transmitting power plus data. So you may just be curious, like, well, how do we actually get the power and the data on the same conductor? So this is, I think, a good illustration. You basically see that the DC power is superimposed on the center tap of the transformers in the device. You can see the PSE there, which is an Ethernet switch. And then we have basically 2 pair sets, and we're going to refer to them two pairs, a pair to transmit and you have a receive pair, or a return path, if you will. So now we're utilizing all 4 pairs or 2 pair sets in a cable for those higher level powers. Matter of fact, class 7 and class 8 to be exact. So the next thing is, you notice those twisted pairs in that previous slide, and I didn't touch on it, but in that table prior to that, but you may have noticed the DC loop resistance. And basically what that is the resistance of a copper pair. And this is very important. And this is important whether you're doing PoE or whether you're utilizing powered fiber. So the reason for that is, first of all, I want to point out some seemingly contradiction between the TIA 568 standard and the IEEE PoE standard. First of all, the 568 standard states that for category 3 through category 6A, the DC loop resistance for channels should not exceed 25 ohms at any temperature from 20 to 60 degrees C. So basically what you see there at the top is the TIA definition of a loop resistance. And that's one pair. So it's basically the round trip, if you will, goes the trip down one conductor and then the return path on the second conductor, 25 ohms. So what we have in the PoE standard defines it as for the current standard is a maximum of 12.5 ohms, or half of what the TIA says. And the reason for that is there's no contradiction, it's really the same. And it's basically 2 pairs. So that the power is carried on 1 pair and then the return path is on a second pair. So basically we're doubling the amount of copper. So the more copper, the larger conductor, if you will, the lower the resistance. So that's the difference for the 25 versus the 12.5. And that's very important. We're going to use that in our calculations a little bit later. One thing I did want to point out is this 100 ohms, and it says this is channel resistance. Basically what the channel is, it includes not only the horizontal cable, which is limited to, it's a maximum of 90 meters, but it also includes the connectivity, such as the patch panel in the telecommunications room, excuse me, and then the work area outlet, and then also the patch cables. So that's a total of 100 meter, and those components comprise our channel. And then one example is, you can see that loop resistance, 600 milliamps. The reason why I chose that number is because that was for a class 4 power, which is basically 30 watts at the PSE, 25.5 watts at the device. So you may have noticed that on the table, but if you didn't, we basically have a 4.5 watt power loss. And the reason for that is because class 4, the power is carried at 600 milliamps of current. So for example, if you multiply 600 milliamps times our 12.5 ohm loop resistance, you have a 7.5 volt drop. If you multiply the 7.5 times your current, you'd get the 4.5 watts, or you could also just take the current, square it, and multiply that by 12.5 ohms, and you see we still get that 4.5 watts power loss. And again, the reason for that is because of the loop resistance, or the resistance of the copper conductors in the cable. And so, and also I will note this, that as current increases, you also have more temperature increase and higher loss as well. So I want to look at one more example for PoE, just how we actually come up with these numbers. And you may say, well, I thought you said this PoE is plug and play. You don't really have to know all this. Well, that is true. Basically, what you could do is, if, say, for example, you know your PD or your power device supports class 8 power level, which is the maximum. In this case, class 8 for the PD would be 71.3 watts, or if it has that optional extended power mode, it could actually support up to 90 watts of power. But the reason why I think it's helpful to understand, like, why do we have these limitations? How do we arrive at these power levels? Because when you start deploying powered fiber, you're going to be utilizing some of this math, if you will, or we have some tools to help you with that, but it really helps to understand it. So the first thing is we're going to do is we're going to calculate what our power, how we come up with our power levels at the PSE. And you may recall this Ohm's law wheel that we showed you at the beginning. We're going to do a simple math. Basically, we're going to take our minimum voltage level for class 8, which is 52 volts, by the way, and we multiply that by our maximum current of 866 milliamps, and we come up with 45 watts of power. And again, that's per pair set. That's for two copper pairs. So we're carrying basically 45 watts on each pair set times 2 pairs, because 2 pair sets, so we have 4 pairs in the cable. So we're able to carry 90 watts of power to our device. Now, we obviously, as we mentioned, we have power loss in that 100 meters of cabling. So for example, how do we come up with that power loss? Well, we know that our maximum current at our minimum voltage there of 52 volts is 866 milliamps. We multiply that again by our 12.5 ohm loop resistance, and we see that we have a voltage drop of 10.82 volts. We can take that 10.82 volts, multiply it by our current once again, and we see our power loss budget. We can derive that at 9.37 watts, multiply that by 2, because our 2 pair sets. And we have a total power loss of almost 19 watts. So basically, even though we have 90 watts at our device, at our PSE, we're only able to deliver a little bit more than 71 watts to our PD, if you will, over 100 meters of cable. So the next question you may have is, well, where does all that power go? It's basically dissipated as heat, which has other negative effects, such as on our cabling bundling, which we're going to look at next. One thing I wanted to point out is back in 2017, the National Electrical Code included or introduced section 725.144, which was basically laid out requirements for transmission of power and data. And without elaborating too much, it kind of caused some confusion or more concern. And so the good news is, in 2020, the 2020 edition, it actually added some clarification, which I was very happy to see. One of those is it states that compliance with, and this is pretty much verbatim out of the code, compliance with table 725.144, which we'll look at in just a moment. it says shall not be required for installations where conductors are 24 gauge or larger and the rated current per conductor of the power source does not exceed 0.3 amps. So basically, what that really means is that, well, first of all, most copper conductors, especially for the horizontal cable that we're talking about, from category 5E up to cat 6A, they're all generally 24 or 23, but the standard states that they can be up to from 24 to 22 gauge. That's the solid conductor horizontal cable. So really, when you look at that, and then that 0.3 amps, that's per conductor. So that for a pair, that would be 600 milliamps. So really what we're saying is classes 1 through 6 up to 60 watts, this table doesn't really apply to that because you would be in compliance. The other statement that it's included, it's an informational, this particular informational note among several others. This informational note states that it says TIA TSB 184-A 2017, which is basically this document is guidelines for supporting power delivery over balanced twisted pair cabling. So see this document for information on installation and management of balanced twisted pair cabling supporting power delivery. So basically what that means is it's referring you to the TIA document for additional guidelines. It does provide this next table that we're going to look at. I'll just go ahead and move there right now. And this is really for bundling requirements that we're talking about. And I'll just say this, that first of all, the National Electrical Code is developed for safety concerns. And so obviously the TIA documents, they don't disregard safety. It's very important, but they're standards designed around performance. And so these two are not exclusive one of another, but you're going to see some comparisons in the next couple of slides of the TIA TSB 184 document. But basically all that to say that the standard cable is in compliance with these bundling limitations in the table 725.144. I just want to point out a couple of things that are very important. First of all, I just want to kind of explain the table. Basically what it is, it's showing the current capacity of per conductor, and I'll just go ahead and mention that right now. These values are per conductor again, so you have to multiply that by 2 to get your per pair or pair current limitation. So what it shows is there's basically 4 different wire sizes. These are conductor size engaged from 22 to 26. And then, by the way, 22 being the largest, 26 the smallest. And then for 3 different temperature ratings. So cables have various temperature ratings. The minimum requirement is 60 degrees C. So basically what we're showing is we're showing bundling sizes from 7 up to 19 to 37, 61, 91, and up to 192 cable size bundles. And so, for example, if you look at, you can see my cursor here, for the maximum bundle size in this table of 192, if you look at for a minimum 60 degrees C rated cable, the maximum current per conductor is 450 milliamps or 900 milliamps per pair. You may recall in that class 8 example, the maximum PoE classification, which was 90 watts of power at the PSE and up to 71 watts at the PD, you may recall me saying that our maximum current was 866 milliamps per pair. That's 433 milliamps per conductor, or 0.43. So that's well within this maximum of 0.45 or 450. So really, the standard 60 degree C cable is definitely in compliance with the for horizontal cabling with the NEC. And again, the values that we're going to look at next in the TSB 184 are per pair. And also, I'll just go ahead and say this: the current, basically, this table is actually listing the bundle sizes and references that shows 3 different values. So basically 600, 720, and 1 amp or 1,000 milliamps, if you will. And the reason for that is the first 6 classifications up to 60 watts, the maximum current is 600 milliamps per pair. Class 7, which is 75 watts at the PSE, and the latest standard is just a little over, it's 721 milliamps. And then you may recall that the maximum for the Class 8 is 866, but the standard, the TSB 184 document, the testing was done at 1 amp, worst case. So just want to point out, for example, this is important as well, the difference between the NEC table and the TSB 184 is the TSB document also lists different values for bundle cable in air and as well as conduit. So you may notice, for example, in air here, there's about 30% less, your bundle size is about 30% less in conduit as air. And the reason for that is really just the restricted airflow and the less heat dissipation. And so approximately 30%, if you look across the board there, you'll see that. And so also you notice that we're listing conductor sizes up to 28 gauge. And the most recent 568 standard actually allows for 28 gauge patch cabling. So that's important to note. It's also important to note that as you look at these bundle sizes, for example, 28 gauge compared to say Cat 6A, they're substantially, your bundle size is substantially smaller. And again, generally for your Cat 6, 6A, we're talking horizontal cabling, where you might have larger bundle sizes, but then you get into your patch cables, they're probably generally smaller anyway. So the next thing is this table looks identical to the previous table, but the previous table, the ambient temperature was 20 degrees C. This table is 30 degrees C. And again, I don't know if I mentioned, but when we looked at the table 725.144 from the NEC, that was also based on an ambient temperature of 30 degrees C. So the key thing I want to point out here is that as you look at these conductor sizes, first of all, for the 10 degree C increase, you notice that, say for the same example, Cat 6A, previously the maximum bundle size in air was 101 for 1 amp, but now it's 96. That's about a 5% reduction. And again, that's just due to that 10 degree ambient temperature increase. And also you notice that the titles in the, is the maximum bundle size for a 15 degree C temperature rise. So really, we want to limit our temperature rise of the cable to 15 degrees C, and the reason for that is really to prevent long-term degradation of the cable and so forth. The other thing is, when you're planning for new installations, it's really important, the standard recommends, and we recommend that Cat 6A or higher be utilized. And the reason for that is, you notice in the NEC standard, it didn't differentiate between performance categories. It was basically based on conductor size. But you notice in the TSB document here, it lists category 5E, 24 gauge, category 6, 23, as well as Cat 6A at 23 gauge. And those are typical conductor sizes for both 6 and 6A category cables. But you notice that there's a substantially higher bundling capacity, about 25% for 6A versus category 6. And the reason for that is because due to the construction, not only the conductor size, but just the overall construction of Cat 6A cables. One is the larger OD of Cat 6A, and the reason for that is primarily due to mitigate alien crosstalk. But the added benefit is it provides this better heat dissipation property, so you can actually increase your bundle size. So again, that's another reason why we recommend category 6A or higher if you're planning to deliver, especially higher powered, the BT standard 90 watts. So that's very important. So just to kind of recap some installation guidelines. Again, higher categories of cable with larger conductors have lower DC loop resistance, and that helps minimize system losses and also reduces your temperature rise. By limiting the cable temp rise to 15 degrees C, you're minimizing long-term degradation of the cable. Lower resistance, again, you experience lower power loss. You're able to deliver power more efficiently. And also going back to the 15 degrees C temp rise, for a typical 60 degree rated cable, basically your ambient temperature would be limited to a maximum of 45 degrees C. And this is important to note too, that's for lengths of 1 meter or greater. So the question sometimes comes up like, well, what if I'm going through a firewall, for example, I'm using FireStop, and I have a higher temperature rating, does that apply? Per the code, per the standards, so long as that distance doesn't exceed 1 meter, it doesn't, so you can have higher temperatures at less than 1 meters, but above greater than 1 meters, yes, it does apply. So the next thing is we've kind of laid the groundwork, the foundation, I think, a good foundation for getting into powered fiber. So what exactly is powered fiber? Again, we all use the term, we kind of explained it, it's hybrid cable. It's basically fibers utilized for data transport, and then at least it's a cable with at least 2 copper conductors for delivering DC power. A key advantage of powered fiber is it's not limited to 100 meters as is PoE. That's a tremendous advantage as you're delivering or deploying fiber deeper into the network, and you've gone well beyond that 100 meters. But the distance is limited as far as your selection of powered fiber cables by your voltage drop and conductor size. So obviously you can't go the distance of fiber, for example, but especially we're talking single mode, but you can go well beyond the 100 meter distance of PoE. The other thing is power is delivered, and these cables are typically constructed of 12 to 22 gauge copper conductor. Again, the power is delivered over separate larger copper conductors, and I mean by separate larger copper conductors as compared to the typical 24 or 23 gauge conductors utilized in category cables. And also those copper conductor sizes are basically spelled out in the UL 13, which is power limited circuit cables in table 5.1. One thing I just want to touch on too, or mention is, because we're going to see this in the next couple of slides, is the copper conductor resistance. Basically, you can see 12 gauge down to 22 gauge. For 12 gauge, for example, these are 1,000-foot lengths. Your copper conductor resistance at 20 degrees C temp is 1.6 ohms. Down to 22 gauge, for example, it's basically 10 times, 16.1 ohms. So you have a 10-fold increase from 12 down to a 22 gauge copper conductor. And then, and we'll look at the examples of basically power efficiency, and the maximum distance you can go with those different conductor sizes. So, but first, what are some of the design considerations when deploying powered fiber? One is your power device. How much power does this device consume, and what is the maximum current draw? Because as I mentioned, loop resistance plays a very important factor, but as current increases, you have greater losses as well. Also, our power source. We obviously have to ensure that our power source has the adequate power to be able to supply the power to the device. And again, I mentioned that typically we're going to be utilizing a class 2 power supply, 100 volt amp supply. Basically, the maximum voltage is typically 57 volts at 1.75 amps max. And then our voltage drop and our power loss budget, which we're going to look at how to calculate that. And then the very important consideration is our conductor size of our powered fiber. What size conductor do we need to go for a certain distance or a certain power requirement? So obviously there's trade-offs. We can carry more power at shorter distances, or we can carry greater power at shorter distances, or lower power at greater distances. So I hope I got that right. So again, there's really, you have to kind of optimize, well, what are my needs? So for this example, we're going to look at what is my maximum distance for a known power level? Say, for example, I have my class 2 power supply to my equipment room, for example. I have a power device, and in this case, I know that my power device, I'm going to power it at 48 volts. It can accept a maximum current of 1.75 amps, and I need to deliver 84 watts of power to this device. So based on that information, I want to calculate which conductor size should I choose for my hybrid cable. First of all, what we're really after is we want to determine that resistance, that loop resistance for these various distances for that power. So the first thing we're going to do is we figure out what is our power loss budget. And there's other ways you can do this, but one is, so we know we have approximately 100 watts at our device, so we're going to deliver 84 watts. So we have do the math, we have 15.75 watts in our power loss budget. So 15.75 watts, we can divide it by our maximum current of 1.75 amps. We square that, and we get 5.14 ohms. So that's the magic number there. Another way of doing that is we calculate, we know we have 57 volts at our source. We want to deliver 48 volts, so that gives us 9 volts voltage drop. So we could take 9 volts, divide that by our maximum current, and we get that same 5.14 ohms resistance. So the next thing is that table we saw before, copper conductors. Basically 12 gauge, we have 1.6 ohms at 1,000 feet. So that's basically we want to convert that to, okay, how far can I go for if I only have 5.14 ohms, or if I do have 5.14 ohms? Well, one way of doing that, we'll just look at 20 gauge, for example. 20 gauge copper conductor at 1,000 feet is 10.1 ohms. So the way we could come up with our distance is we take our 5.14 ohm budget, if you will, divide that by 10.1 ohms, and we can multiply that by 1,000, and that gives us 509 feet. This is very important. That 509 feet, we need to divide that in half because we have to take into account the return path. So basically that 509 feet is the distance from our source to the device and then back again. So we divide that, we have 254 feet physical distance. So these are the physical distances for delivering this amount of power over these copper cables, so or conductor sizes. So you can see with a 12 gauge, we could actually go up to 1,600 feet, 1,606 feet with 12 gauge, and then at 18 gauge, for example, we could go up to 400 feet. So it's still well beyond the 328 feet distance of PoE. So and also you notice, we want to limit if we needed to deliver that power at 48 volts, then we have a 9 volt drop allowance. You notice as we get down to 20 gauge, we're actually going to exceed that voltage drop. And I will say this, that most devices usually have a lower voltage level than 48, but again, you just have to look at your spec sheets on your device and know what the operating parameters are. And then you get down to 22 gauge, you see that we're at 160 feet, much lower. So basically, again, from 12 to 22, that's 10 times the resistance, 1/10 of the distance that we can carry that power level. So the next example is maximum power, maximum power for a known distance. In this example, we're using the same class 2 supply, and in this case, I chose 100 meters or 328 feet. So how much power, if I know the distance, but I'm not really sure, maybe today I know that I have this device that requires 84 watts, but in the future, I'm not sure, what I may connect at that same connection point. Maybe I'll replace this device with a higher power level. So what I'm going to do is, again, but keep in mind, this 328 feet, we have to multiply that by 2 because we have to account for our return path. So we're really wanting to figure out what that resistance is for 656 feet. So what we do is we know that we can calculate our power loss budget. One is, well, first of all, we just get a resistance simply by taking our 1.6, for example, at 12 gauge. We can multiply that by 0.656 for 656 feet, and that gives us our resistance, which is 1.05. Or, for example, 22 gauge, we can multiply that and get 10.56. The next thing is we multiply that resistance by our maximum current, and then, or current squared, if you will, or we can just take our voltage drop and multiply by our current. And you can see the various voltage drop levels, and then we can take that voltage drop, multiply it by our current, we get our power loss. So either way, we're seeing for 12 gauge, we have a 3.2 watt loss. Again, 10 times that for 22 gauge. So really, we're looking at the efficiency. For a larger conductor, for 12 gauge, for example, we're able to deliver 96.5 watts of power. So that's basically a 96% efficiency rating. Whereas we're losing a third of our power with 22 gauge. You know, we're only delivering 67 watts. And again, if that 48 volts is critical, you know, if that's our cutoff voltage, then we can only really use an 18 gauge or larger conductor size, because we would be losing more, we have a greater voltage drop than 9 volts for these 20 and 22 gauge. So again, you can see, you know, basically there's situations where you may know, I don't necessarily know how far I'm going to be going, but I know I have these devices that require a certain power level. And then others, I know I have fixed distances, but I'm not really sure. I want to basically size my conductors for future growth. So, and by all means, that's what we would encourage you to do, is plan ahead. So, you know, I went through this math. We did a lot of math, you know, to do these calculations, but we do have some tools on our website that basically kind of take the guesswork out, or, you know, help you out to do that. This is an example of our remote power maximum distance calculator, and this calculator can be found on our occfiber.com/slimline hybrids landing page. Basically, what you do is you enter your ambient temperature, which again, as we've discussed, it does impact your loop resistance and the amount of loss and so forth, and ultimately the maximum distance that you can go. And then you enter your supply voltage, which typically, again, for class 2, it's going to be 57 volts. And then your cutoff voltage, 48 volts is what we've been using in our examples. And then 84 watts of power, for example. I use this, you can see the calculator, because that's what we discussed previously. And you can see these that we manually calculated. You can see the calculator, you just click on the calculate button and it spits out these numbers for the various conductor sizes. So I encourage you to visit that and play around and use the calculator. I think you'll find it helpful. One thing is, I did mention this at the beginning, you know, I tried to emphasize this, you know, in the title, you know, we said powered fiber versus PoE versus powered hybrid fiber, but again, these applications or technologies are really complementary. For example, this is an illustration of a passive optical LAN network, and you see here in the equipment room where you have your OLT and then your class 2 power supply. We're utilizing a hybrid slimline hybrid cable to deliver data over the optical fibers and power over the copper conductors to an ONT, which would, in this case, is located in an active zone enclosure. So basically what we're doing is we're providing power to this ONT, which happens to have the capability of providing PoE to those connected devices, to its RJ45 copper ports. So up to 100 meters, of course. So in this case, you can see a camera and an access point that we're powering from our ONT. But it's obviously important that the amount of power that we provide over our powered fiber, if you will, we have to provide enough power for the device as well as the PoE that it's going to provide to these connected devices. So again, it gives you just more flexibility in your network design. This is another example. You know, in that previous example where we're calculating what is the most power we can deliver for various conductor sizes. Well, you know, you may recall, you know, we said for 12 gauge, we're only losing 3.2 watts. So we're in effect able to deliver over 96 watts of power to the device. In this case, this particular device requires 16 watts of operating power. So this 96 watts minus the 16, it leaves us an 80 watt power budget available for PoE that it can provide to these other devices up to 100 meters. So, and that was based on, again, you know, our example of 328 feet or 100 meters. So in effect, what we've done is we've provided power over 100 meters of powered fiber to an ONT, and now we can provide power up to, for an additional 100 meters to these devices. And by the way, most of these devices that we're going to be providing remote power to, you know, cameras, access points, they have RJ45, you know, copper ports, you know, and they're generally PoE capable. So they just lend themselves to utilizing PoE, obviously, and less expensive as well. So again, I think this is a good example of how these technology, powered fiber and PoE, are complementary. So just to summarize, you know, as I mentioned at the beginning, PoE is a standards-based plug-and-play application, if you will. You know, there's a lot of handshakings, and it takes a lot of the manual calculations and whatnot out of it. And it's based on a worst case 100 meter distance limitation. So it always factors that in, assumes worst case. But powered fiber, it's more flexible, but it requires some additional design considerations, a little bit more homework, if you will. Powered fiber extends the reach of remote power beyond 100 meters. That's a key benefit of utilizing powered fiber and a necessity in many cases. And finally, powered fiber and PoE can coexist as complementary solutions. So we're not really advocating one over the other. We're recommending, we think you'll find that there are definitely situations or environments where they both can be utilized. So with that, I will turn it back over to Eric.
Awesome. Thanks, Jamie, for sharing that great information with us today. As you all can see on this slide, we have a number of resources, some of which Jamie mentioned, that will provide information on our various products and services to complete all of your solutions. These materials also verify reasons why to look for OCC for your fiber, copper, and hybrid cable and connectivity needs. All of these resources will be included in a follow-up email for your convenience. They can also be found on occfiber.com. Please make sure you are following our various social media channels on here. We have YouTube, Facebook, LinkedIn, and Instagram. There we post many things as far as like OCC news, new products, promotions, webinar information, and a whole lot more.